This is John Black, super chemist, here to talk about protonation and what that means. What is the deal? First, you have to learn a couple things here. Um, any atom has an inner core with nucleons and an outer core or an outer whatever with electrons. Now, the nucleons inside here are protons and neutrons. All right, that's why I gave them different colors. This is carbon. It's number 6 on the periodic table, so it has 6 protons, and I put in 6 neutrons, okay, to even it out. And that's the way most people, and then there's 6 electrons to balance out the protons. And that's how most people perceive the atom. And this is chemistry, not physics. They don't actually orbit the electrons. They're just a wave of probability. You know what I mean? And we're not going into that. This is chemistry, not physics. Um, so this is what you, and now if you make that into a positive ion, right, you would remove one of the electrons. Now that's positive, okay? But it still has a bunch of protons and neutrons. Now look at this hydrogen, same deal. It's number 1 on the periodical table, so I gave it 1 proton, 1 neutron, and 1 electron. If I take the electron away, you'll have a proton and a neutron. Now, why is a hydrogen that's positively charged, why is that called a proton sometimes? Okay, this is why. Most hydrogen, I'm making up numbers here, I want to say 98, 99%, but at least 90% of all hydrogen in the universe does not contain a neutron. It only contains a proton. So when you take that electron off, all you're left with is a proton. That's why. What's the difference between a proton and a positively charged hydrogen? Nothing. They're the same exact thing. Exactly the same thing. And that's why some people refer when they're putting a hydrogen on something, sometimes they're like, well, they call it a proton. I do that a lot. Remember, we just said a hydrogen that had its electron stripped away is only left with a proton because there is no neutron. So you can just call it a proton. Now look at this reaction. It's an acid and a base, right? Makes salt water, right? How does that happen though? Well, see these lone pair electrons on the oxygen? Um, you can see these arrows. Anytime you see curvy arrows, that tells you they have to start where the electrons are because that's what they're telling you, where the electrons move. So these electrons move to this positive hydrogen, right? These electrons jump over to here, and what do you end up with? You end up with a negative chlorine, right? Now, if these electrons grab this hydrogen, right, you end up with water. Then sodium comes off as positive, and your chloride is your negative. But what did you do? You protonated that. Same here. This is an acid and an alcohol, right? I had a video where I made ethyl bromide, right? This is basically the mechanism. Same thing. You got electrons here. They move over and grab this hydrogen, right? The hydrogen leaves the electrons from this bond to the chlorine. So you end up with a negative chlorine and a water on this alkyl group, this hydrocarbon chain. Now, this is a good leaving group. Water loves to be by itself. It's water, so it's nice and stable. So this chlorine takes its negative, come up here, does an SN2, and the water leaves, and you end up with your alkyl chloride. But the point I'm trying to make is over here. This is just secondary. The point is that you just protonated this alcohol, this N-propyl alcohol. Okay? Next example. Same thing. We're going to switch it up with the bromide. It's always the same. It's an acid. It's got a proton. Here's your base. It's water. Water can be an acid or a base. It's got these electrons, grabs the proton, leaves the electrons here for the bromine. You end up with a hydronium ion and a bromide ion. Okay. But the point is, you protonated this water, right? Next example, a double bond, an alkene. As you know, this is a lot of negative electron density. Electrons jump off, grab this hydrogen. The hydrogen leaves these electrons for the bromide. You have a negative here and a positive here. Then your bromide can come in. Bam. You got a, what is that? 2-bromo propane. But the point is that you protonated this double bond. That's what protonation is, basically. First of all, just so you know, when you do put like hydrobromic or a hydrogen bromide or hydrogen chloride in water, what actually makes the acid is the hydronium ion. The electrons, like I said, grab this proton and leave the electrons a negative bromide, right? This becomes a hydronium ion that's positive. It's very reactive because oxygen is electronegative. It doesn't like to be positive. So anyways, after that happens, let's say you're trying to brominate your alcohol to make an alkyl bromide. Now, this is what actually reacts with this, okay? And I want you to look at when these two molecules get close together, right? Here they are even closer. You can see that, I mean, a line is just 2 electrons, right? So all I have to do is change these 2 electrons into a bond and change this bond into 2 electrons that are up here. See, just like that. Then this can split off, and then you can do your SN2 with this and make your alkyl bromide. But my point is you're just basically exchanging. See how it comes up there? Think of it as a magnet. You know what I mean? This magnet gets so close, it snags the proton. You know what I mean? Just like any magnet would. And this wants these electrons, so it takes them. Anyways, I don't want to get too in depth in this. I just wanted to let you know what protonation is and why a positively charged hydrogen and a proton are the same exact thing. Okay, why don't they call it hydrogenation? You know what I mean? Because you're not actually adding hydrogen, you're only adding the proton. You're leaving the electrons to the whatever's left there for the anion. Anyways, have a great day, and always remember, science is great.